Hey guys, welcome back. So today we're going to look at frequency and transient response in capacitive and inductive circuits. And when the switch is, this DC current is going to go and charge the capacitor. And the capacitor voltage at any period in time is given by this expression that I've written on the right hand side right here. So this expression gives the capacitor voltage at any point in time after the switch is closed. Okay, so let's go ahead and examine what each element means. So here VC is your capacitor voltage. So this is what we're measuring across the capacitor, and VC at 0 is the initial voltage. So if the capacitor has never been connected to a DC source, so it's going to hold charge. I mean, if it has been connected, it's going to have some charge. If it's not going to have any charge. So this depends on initial charge or initial voltage across the capacitor. So that's at time t equals 0. And this time t equals 0 is when your switch is closed. So that is when we start measuring, or that is when the event is set to occur and everything else moves forward from there. So at time t, this switch, I'm closing it. That's going to enable the current flow right there. And this term e to the power of minus t by RC is an exponential term. Let's see what it means. So RC, the determining factors here is the value of your R and C. So the product of R and C is known as tau, or time constant. So this time constant will determine how fast or how slow your capacitor voltage is going to rise. And this voltage here is the supply voltage that is given by the power source. And once again, we have another exponential term. This time it's 1 minus e to the power of minus t by RC. So when we have circuits like this, the important thing to remember is when the switch is closed, that is your t equals 0. Alright, so that is when the event happens. And you got to remember this expression. And let's move to the case of an inductor. Once again, at time t equals 0, the event occurs, and by that event, I mean the switch is closed. And once that event occurs, once again, we are going to have a current that's going to flow. So if you remember, if you watch the inductor video, you remember inductor is basically some conductor wound around the core. That's going to prevent the change in the value of current. So initially there's going to be 0 current, and when the switch is closed, it's going to prevent the rise in current, but ultimately it's going to behave like a short. So that behavior in current is determined by this expression. So this is current in the circuit, and once again you see the I at 0 value. So this is the initial current. So this is if there is already some current flowing in the circuit, so that is going to be this value. And here we don't have RC, but instead we have RV by R value. Sorry, R by L. If you remember these two expressions that I have circled in the yellow, way to go. We can solve all problems. We just need to know what each terms mean, and sometimes it can get confusing. So without any further ado, let's go and solve some problems. So we come to our first problem. In our first problem, we have a statement saying calculate capacitor voltage after 5 minutes. So what is happening at our t equals 0 is initially the switch is at this position, and the 20 volt supply right here is going to be charging the capacitor. So at t equals 0, the switch flips, and now your capacitor is going to maintain the flow of current through the resistor, as shown here in the yellow. Okay, so let's use that expression that we just saw for the voltage, but before that, let's go ahead and do something. Let's find our tau value. So that is our RC, and here our R value is 100 kilo ohms. So I'm going to write 100 into 10 power 3 times our capacitor value is 1 millifarad, so that's 1 into 10 power minus 3. So 10 power minus 3, 10 power minus 3 cancels, and our RC value is 100. And we're being asked to calculate the capacitor voltage after 5 minutes. Now remember, 5 minutes is not in the standard units. So in seconds, that is going to be 5 into 60. That's 300 seconds. So we're being asked to calculate VC at 300. So this is what we are being asked to calculate. Okay, now let's go ahead and write down that expression. So the expression for that was VC at a certain time t is VC at 0, that's the initial capacitor voltage, e to the power of minus t by time constant RC, plus the supply voltage 1 minus e to the power of minus t by RC. There's a logic behind this expression, but right now you don't have to worry about that. So we're being asked to find VC at 300, and this is going to be VC at 0. So if you remember, it was connected to a 20 volt supply. So after 5 time constants, usually the capacitor gets charged to 98% of the supply. So here it's going to get charged to 98% of 20 volts. So I can just write it as 20 volts. Okay, and e to the power of minus t value is 300 divided by RC, that we found to be our product of R and C was actually 100. Okay, so 100. All right, now the next term, this term is going to be equal to 0. And why is that? Because if you look at this V is the voltage supplied by a battery, right? And if you look at the circuit here, once the switch is flipped, we have just one resistor, 100 kilo ohms, and one capacitor. That's it. So where's the power being supplied here? There you go. That's why you have this term 0. Okay, so let's go ahead and simplify this. So that's 20 e power minus 3, and that is going to round up to 0.995 volts. So that is my final answer. So if you switch, the graph for this is going to go somewhat like this. So initially this capacitor is going to be, and the 20 volt supply is going to be turned on. So the capacitor voltage is going to rise like this until it reaches 20, and this is going to be at least 5 time constants. So it's going to stay at 20, and once the switch is flipped, now there's no more battery supplying the power, and the capacitor is going to discharge, and it's going to discharge like this. So once the switch is flipped, so this is your time 0, and at 300 seconds it's gonna be 1 volt right here. So it drops from 20 to 1 volt. So that probably gives you an idea, so if you have a capacitor in the circuit, just when the switch flips, after 300 seconds it goes from 20 to 1. Right, let's move to the next problem. Calculate capacitor voltage for t greater than 0. So here, what's happening here, I've tried to show you in the circuit, is we have a 10 volt battery that's supplying DC power, right? So I'm going to show it here in green. So it's supplying DC power this way, and also it's charging the capacitor this way. Now at certain time t equals 0, what's going to happen is this switch is going to open. Now it's the same as our previous case. What happens when the switch opens is your capacitor in the circuit is going to maintain the current flow. So now the current is going to flow this way. So this branch is no longer existing, and it's going to flow that way. And we got to find the capacitor voltage for t greater than 0. So it's a very simple problem. Let's write the expression first. So the expression that we saw was VC at any given time t is equal to VC at 0, time t equals 0 when the event happens, e to the power of minus t by your time constant RC, plus if there is any battery supplying the voltage, that voltage, times 1 minus e to the power of minus t by RC. Okay, let me rewrite that. E to the power of minus t by RC. I'm going to write it here. Vc of t greater than 0 is, so what is the initial voltage on the capacitor? What is the voltage being supplied? It's 10 volts. So after 5 time constants, the capacitor is said to have 98% of 10 volts. So we can safely assume that it's been charged for a while. So this this circuit was in this condition. So the capacitor had been charged. Okay. So we can say this was 10 volts and e to the power of minus t by RC. So what is our RC value? So I'm going to write it here. Our RC is 10 kilo ohms, so that's 10 into 10 power 3. And our capacitor value is 200 microfarads, so that's 200 into 10 power minus 6. So our RC value gets to 2000 into 10 power minus 6, that's just 2. Okay, 2 seconds. So e to the power of minus t by 2. And once again, like in the previous case, after time t equals 0, the switch is going to be open, so there's no more battery in the circuit to provide a power supply. So this is going to be 0. So our final expression is just going to be Vc for t greater than 0 is going to be 10, oh sorry, that was an e. So it's going to be 10 e to the power of minus t by 2. Alright. So in this circuit, we took the main expression and we simplified it to get this expression. So for any engineer coming in, we can say, okay, if my battery fails, the capacitor is going to discharge at 10 e power minus t by 2. So at this point in time, I'm going to have this voltage. So is that safe? Is that going to damage the circuit? So that's all questions you will encounter in the real world. So that is why these concepts are so important. Okay, now let's go to inductors. So if we remember, let's go back and look at this formula for inductors. It's for rise in current. And where we had RC, this time we have R by L. Okay, so then solve this problem. So it says calculate current in the circuit if switch closes at t equals 0. So t equals 0, this switch is closed and DC current will start flowing, but it will not reach the full value because there is an inductor in the circuit and it's going to resist the change in current. It's not going to stop it, it's going to resist it. There's a difference. Okay, so it's once again a simple substitution problem. So let's go ahead and write the equation for that. So it's I of t is I of 0 e to the power of minus R by L times t plus V by R. I'm gonna write that here because I'm out of space, plus V by R 1 minus e to the power of minus R by L times t. Okay, so this expression is going to become my initial current. So before the switch closes, it's a completely open circuit, so there is 0 current flowing in the circuit. So that this entire term becomes 0. So this entire term becomes 0. Now let's go and solve for the next term. So once the switch is closed, we have a voltage in the circuit, 10 volts. We have a resistance, 1 kilo ohm, and we have this expression 1 minus e to the power of, what is R by L? So that's 1 kilo ohms. So that's 1 kilo ohms divided by 2 millihenry. So that is 0.5 into 10 power 6 or 5 into 10 power 5. So it's going to be E into 5 into 10 power 5 times T. A little bit messy. So let me write it somewhere else. Okay, so the very same expression, I have taken it, I have written it in a fresh slide. So if we simplify this, we're just going to get I of t is equal to 0.01, that is 10 by 10 power 3, 1 minus e to the power of minus 5 into 10 power 5 times t. Okay, so that is the expression for current. So at time t equals 0, the current starts flowing. At t equals 1, if you substitute 1, you get the answer. So that is the value of current. At t equals 2, you substitute the value of 2 and you get the answer. So that is how you find the value of current if you have an inductor and the switch is closed. Okay, so this is basically something you would see in your DC motors where you have series windings, but that's fine for now. I'm not going to go too deep into that. Alright guys, welcome to our last problem. This is quite a lengthy problem, so let's go at it step by step. Okay, so it says there is a circuit like this which has a voltage source in series with a resistance, and it has two branches. One branch has this 5 ohms and 1 Henry. So this is 1 Henry. Okay, so it has an inductor and a resistor, 1 Henry. And another branch has just one resistor, 10 ohms. So it says calculate current 10 time constants after opening the switch. So the switch here is going to open at t equals 0. And after that, the circuit is just going to be, we have your 5 ohm, we have our inductor, and we have our 10 ohm resistor. Okay, so this is going to be our circuit after time t equals 0. And we're being asked to find the current after 10 time constants. So the current, if you just look at this circuit, you can say the current is going to die down, because once you remove this supply, there is no more potential driving the current. So the current has to drop to 0. But because there is an inductor in this circuit, it's going to resist a change in current. So it's going to resist a rise in current and as well as resist a change in current. If you look at our transient expression for inductors, so let's see, we had, yep, there it is, right there. So you had I of t, let's say at 10 time constants. We have initial current at 0, e to the power of minus r by L, that is our tau value, times t, and v by r and times 1 minus e to the power of minus r by L. Okay, so we need to find what is I of 0. So when the switch is opened, there is some current that is flowing here, and that current usually drops to 0 if there was no inductor, but we need to find what is that current. So that is going to be our I of 0. So to find out, we're going to have to do a little bit of math. Okay, so let's for now close this circuit, and we got to find what is the main current being supplied by this voltage. Before doing that, I'm going to find the equivalent resistance. So my equivalent resistance is, if you look at it, my current is going to flow through 10. It's going to split into two branches. One current is going to flow through the 10 ohms. The other current is going to flow here. Okay, so it's going to be 10 plus 5 in parallel with 10. So that's going to be 10 plus 5 times 10, 50, 5 plus 3, 15. So that's 3.3. So that's 10 plus 3.3 is 13.34. So that 13.34 is the equivalent resistance. So now we find the current. So the current being supplied was V by R equivalent. So that's V is 10 volts, R is 13.34. So that would be 0.75 amperes. So now we found the main current. Now, but we still don't know what was this current flowing in this inductor branch. To find that, we're going to find what is the voltage across these 2 points that I've marked here at red. So that voltage is found using the voltage divider rule. So using voltage divider, we find that voltage is going to be 0.75, that's my main current, into the resistance that it's flowing through is 5 ohms in parallel with 10, and that is going to be it's going to be 2.5 volts. And now finally I can use Ohm's law to find what is the current through that inductor. So that is going to be my I of 0, which is V by 5 ohms. So that is 2.5 by 5, and that is 1 by 2, that's 0.5 amperes. Okay, so I got my initial current. Now let me go ahead and find the time constant for an inductive circuit, which is L by R, and that is 1 Henry divided by 5 and 10, so it's 15 ohms. So because if you saw our circuit here, it had 1 Henry, 5 and 10 ohms, so it's 15 ohms. So it's just gonna keep it as 1 over 15. Time to write our final expression. So I of t, so it's asking for 10 time constants, so that's 10 into 1 over 15. So I at this point in time is our initial current, I of 0 e to the power of minus r by L times t plus v by r times 1 minus e to the power of minus r by L times t. Now once again, before we do anything, let's look at this term. At time t equals 0, our switch is going to be open, so there's no voltage being supplied here, so this is going to be 0. Alright, so let's go ahead and solve this without that. So it's I of 10 over 15, or 10 time constants. I'm just going to write it as tau. Better way to write that. 10 time constants is I of 0. That what our I of 0 was 0.5 amperes. So it's 0.5 into e to the power of t by tau. So our tau was 1 by 15, t by 1 by 15 is 15. So that I at 10 time constants is 0.5 times e to the power of minus 15 t. Now what is t here? So this is why I skipped that part, is our t is 10 tau. So that is 10 into 1 over 15. Alright, so it's going to be e into minus 15 into 10 over 15. 15 cancels, so it's 0.5 into e power minus 10. That is going to be 22.6 into e power minus 10. Simplify all of this, I would get into 10 power minus 6 amperes. So what this means is once the voltage drops, sorry about that. So what this means is once this switch opens right here, this entire branch does not belong to the circuit. So if there was no inductor, it would just straight away drop to 0. But because there's an inductor, there's going to be some current flowing, and inductor resists the change in current. So you would have, after time constants, still a very minute current of 22.6 microamperes, which is not 0, but it's still some current, and that's only because of the inductor. So if you looked at it for 5 time constants, that would be a totally different expression. I mean, totally different value for that. It would be a higher value. So in a regular DC circuit, what would something drop like this as soon as the voltage supply is cut off? It would drop to 0 because the inductor is there. It's going to drop this way. That is the importance of this concept. Alright guys, just thank you for watching.